Hey everyone, let's see, I want to continue our study of representing functions as power series. Remember last time what we had was the geometric series, and by just knowing this fact, we were able to, by various ways of manipulating expressions similar to this, we're able to find power series representations for those functions. Now, we need a little bit more technology, and once we have that, we'll be able to do more advanced representations of functions. And so here's the next piece of the puzzle. It's called term by term differentiation and integration of power series. So term by term differentiation and integration of power series. And so I'll write it out precisely, but the idea is if you think about a power series as a polynomial that goes on forever, then the formula for computing the derivative or the antiderivative of a power series matches exactly the formula for taking the derivative or antiderivative of a polynomial. So suppose that we have a function f of x equal to some n equals, I'm going to do k, n equals k to infinity, c sub n x minus a to the n with radius of convergence equal to r. And you don't need to write this out if you don't want to, but let me just sort of elaborate on what this is saying, right? So f of x is equal to c sub k times x minus a to the k plus c sub k plus 1 x minus a raised to the power k plus 1, right? And then this just keeps going on forever. But each term is polynomial-like, right? Now, there's two parts of this. The first part tells us how to get a power series representation for f prime of x. So f prime of x is given by computing the derivative of this power series right here, and you do it behaving exactly as if it's a polynomial. And so what it's going to be is the sum n equals k to infinity. Now let's see, if I look at this right here and I'm taking the derivative, what do you do? Well, if it was a polynomial, you'd bring the n down. So this will be n times c sub n x minus a raised to the n minus 1. Take the derivative exactly as if it was a polynomial. And in fact, so let me just, you don't need to write this down, but if I was looking at it right here, what I would get is, so you don't need to write this down, k times x minus a to, k times c sub k. C sub k, x minus a to the k minus 1, plus, all right, what's the derivative of the next piece? Bring the exponent out front, and then subtract 1 from the exponent. And this would keep going on forever. And here's the additional fact, if the original function has radius of convergence r, same thing here. When you take the derivative, the radius of convergence does not change. Same thing with the antiderivative, right? So what we get is that the antiderivative of f of x is going to be gotten from this power series by treating it as if it's a polynomial. And so what we get is the power series sum n equals k to infinity. And let's see now, how do you take an antiderivative? It's going to be c sub n x minus a raised to the n plus 1 divided by n plus 1. And then remember, there's always a plus c, right, when you take an antiderivative. And so you don't need to write this down, but if I was writing it out like this, what would I get? I would get c sub k x minus a raised to the k plus 1 divided by k plus 1 plus c sub k plus 1 x minus a raised to the k plus 2 divided by k plus 2. This goes on forever. And then afterwards you have a plus c. And one more thing to say here, when you take an antiderivative, the radius of convergence does not change either. So ROC, once again, equals capital R. Right, so this is called term-by-term differentiation and integration of power series, and what it says is that when you have a power series representation of the function, you can find the derivative, the power series for the derivative or the antiderivative by taking a derivative as if each, taking it term by term, behaving as if you have a polynomial. Okay, so now let's do some examples. And I should point out that these are going to be our main three tools when working with power series and trying to find representations. We have the geometric series, and we know that we can do substitution. And now we know that we can do derivatives and antiderivatives. Those will be our tools for manipulating given power series to find new power series. So as a first example, let's say suppose f of x equals sum n equals 0 to infinity minus 1 to the n x to the 2n divided by 2n factorial. Now you can show that this holds for all, this representation is equal for all real numbers. In other words, the radius of convergence is equal to infinity. What I want to do is find power series for the derivative and the antiderivative. So f prime of x is going to be sum n equals 0 to infinity. And let's see now, I bring the 2n out front, minus 1 to the n, x to the 2n minus 1, divided by 2n factorial. Bring the exponent out front, subtract 1 from the exponent. Now I can clean this up a little bit by noticing that this 2n over the 2n factorial, there's a little bit of cancellation, and so this is minus 1 to the n, x to the 2n minus 1 over 2n minus 1 factorial, and the radius of convergence stays at infinity. Okay, so there's the derivative. Now let's compute the antiderivative. So the antiderivative of f of x is going to be found by computing the antiderivative of the corresponding power series. So we'll get x to the 2n plus 1 divided by 2n plus 1, 2n factorial plus c. And then we should notice that you can combine this. So this becomes sum n equals 0 to infinity, minus 1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial plus c. Okay, so we're going to use this technique now to find power series representations for certain familiar functions. And so first one I want to do, first example, or next example I want to do, I want to find a power series representation for the arctangent. So let's find a power series representation for the function f of x equals arctan of x. Now, what we need to do is think, okay, what does arctan have to do with anything else that we've learned so far? Well, right, I mean, really all we have, right, so the only thing we have to go with is that, well, okay, so what's the connection here? One thing we know is that the derivative of arctan of x is 1 over 1 plus x squared. And then if we combine that with this fact right here, I think we could put these two facts together with a little bit of substitution to actually make things work out. So here we go. We know that 1 over 1 plus x squared, that's equal to, well, let's write it like this, 1 over 1 minus negative x squared, which is equal to, now I'm going to use our geometric series formula. This is sum n equals 0 to infinity, and it will be minus x squared raised to the nth power. All right, so all I did, we're substituting a minus x squared here, which means substitute a minus x squared here, which is equal to sum n equals 0 to infinity. I'm just going to clean this up a little bit. Minus 1 to the n, x to the 2n. And remember, when you do the substitution, right, what we require is that absolute value of x squared be less than 1. Well, I'm sorry, absolute value of x squared less than 1 means that absolute value of x has to be less than 1. So our radius of convergence is 1. Okay, so what we have now, we have found a power series representation for the derivative of the arctan. And so that means if we want a power series representation for arctan, I should take an antiderivative. All right, so now arctan of x is going to be the antiderivative of this power series right here. So that'll be antiderivative sum n equals 0 to infinity minus 1 to the n, x to the 2n dx, which is equal to, so now let's take the antiderivative. Don't forget the plus c. So we have arctan of x is equal to this. Now the last step is we need to find c. And the way I'm going to find c is I want to substitute 0 on both sides. That'll cancel this part out and we'll be able to solve for c. So what we have is 0 equals arctan of 0, which equals, so if I substitute 0 here, I'll get 0. So that's equal to c. And so final answer, arctan of x is equal to sum n equals 0 to infinity minus 1 to the n, x to the 2n plus 1 over 2n plus 1. And that holds for all x for which absolute value of x is less than 1. All right, so there's a power series representation for arctan. Let's try another example of a familiar function. What I'd like to do is, so let's find a power series representation for the function f of x equals natural log 1 minus x. And okay, so how are we going to do this, or what's the connection between this and geometric series? Well, if I take the derivative of this, right, we'll get negative 1 over 1 minus x. So that's the idea. Is let's work it all out here. So note f prime of x is going to be negative 1 over 1 minus x, which is equal to negative sum n equals 0 to infinity x to the n. So if I want the power series representation for f, then I need to take the antiderivative of both sides. So the antiderivative, well, so f of x equals antiderivative of f prime of x dx, which equals the antiderivative of this, which will be a negative sum n equals 0 to infinity x to the n plus 1 divided by n plus 1 plus c. let's see. Now, the last thing I need to do is figure out who c is. And so once again, I'm going to plug 0 in to both sides. So f of 0, that's natural log of 1, which is 0. So I have 0 on this side, 0 right here equals c, so that tells me that c equals 0. And so what we get is natural log 1 minus x is equal to negative sum n equals 0 to infinity. X to the n plus 1 divided by n plus 1. And now what do we need to know, or we need to finish this off with by including the radius of convergence. Radius of convergence here is 1. All we did was take an antiderivative. That doesn't change the radius of convergence. So there it is right there. Now as an application, check this out. So what I want to do, let's look at natural log of 2, which is equal to negative natural log of 1/2. Just using a rule of logs, right? I can bring that exponent up here. That's equal to, let's see, negative natural log of 1 minus 1/2, which is equal to, okay, so what that's saying is if I put a minus sign out in front and substitute a 1/2, then we get equality. So this is equal to sum n equals 0 to infinity, 1/2 n plus 1 divided by n plus 1. So that's equal to, let me write this in a little bit nicer form, sum n equals 0 to infinity, 1 over 2 to the n plus 1 times n plus 1. So here's what's happening. Make sure I wrote that down right. Yeah, that's fine. Oh, yeah, sorry, I spaced out for a second. So here's the idea. If we were handed this series back when we were studying how to decide whether a series converge or diverge, we could easily show that this one converges, right? Various tests would work, right? Comparison test. Yeah, comparison test is probably the quickest. You can also use a ratio test. We could show that it converges, but we would not be able to show what it converges to. Now, with the use of power series, we were able to show, or we were able to see, that this series right here, not only does it converges to that number right there, natural log of 2. One thing that I want to do, so this is true what I have written down right here. Natural log of 1 minus x is equal to this power series, but we can do one simplification step that makes it look a little bit nicer. So let me write it down here. Sum n equals 1 to infinity. X to the n over n, where absolute value of x is less than 1. So oftentimes in books you'll see it written this way, right? Instead of starting at 0 and having n plus 1 and n plus 1, you can start at 1 and have an n and n. It makes it a little bit nicer. Either one of these is true, and you can use them either way. Okay, for our next example, so let's find a power series representation for the function f of x equals, and it's going to be x cubed over 4 plus x quantity squared. This function looks kind of geometric-ish. The difference is that I've got a power of 2 down here. And so here's what we want to remember, right? If I start off, let's say, with 1 over 1 minus x, and I take the derivative, notice what we get. We get well, negative 1 over, actually it's positive 1 over 1 minus x quantity squared. So to increase a power, you can take a derivative. All right, so we want to use that principle in solving this problem right here. So my starting point, well, let's do it like this. 1 over 4 plus x. That's equal to, well, let's factor the 4 out, so that'll be a 1 over 4, 1 plus x over 4, which is 1 over 4 times 1 minus a negative x over 4. So what we've done then, right, we pulled out a 4, and now what we have is something where we can apply our geometric series formula to. So this is equal to the sum, n equals 0, sorry, there's a 1/4 out there. 1/4 sum n equals 0 to infinity, and then it's going to be negative x over 4 raised to the n, which if we clean this up, it'll actually be sum n equals 0 to infinity, minus 1 to the n, x to the n over 4 to the n plus 1. And notice we substituted an x over 4 in there, which means that our radius of convergence then is going to be 4, right? We need absolute value of x over 4 less than 1. If you solve, that tells us absolute value of x has to be less than 4. Okay, so we've got it. We have a representation for 1 over 4 plus x. That's my first step. Now I'd like to get a square in the denominator, so I'm going to take the derivative. And so on the left-hand side, I will get negative 1 over 4 plus x quantity squared. On the right-hand side, I'm going to take the derivative of this. Sum n equals 0 to infinity minus 1 to the n, nx to the n minus 1 over 4 to the n plus 1. Sorry, I got a little bit crowded here. I'm going to clean this up, but let's remember when you take a derivative, it does not change the radius of convergence. So here's the thing that you can notice, and the book will definitely do this if you're checking your answers. N equals 0 would put a 0 here, so the 0th term is going to be non-existent. And so typically what we do is we recognize, oh, we don't even need the 0th term, so we're going to start with n equals 1 to infinity, minus 1 to the n, nx to the n minus 1 over 4 to the n plus 1. It's not necessary, but the book will definitely do this. All right. Okay, so now I have a power series representation for negative 1 times 4 plus x squared. Let's get rid of that minus sign. And then we'll multiply by x cubed and we'll be done. So if I multiply both sides by a negative 1, what we'll get is 1 over 4 plus x quantity squared is equal to sum n equals 1 to infinity. Now if I multiply through by minus 1, what we'll get is a minus 1 to the n plus 1, nx to the n minus 1 divided by 4 to the n plus 1. Still have a radius of convergence of 4. Last step, I'm going to multiply by x cubed. That's not going to change the radius of convergence either. And so x cubed over 4 plus x squared is going to be sum n equals 1 to infinity minus 1 to the n plus 1. And now if I multiply through by x cubed, adding exponents means that this will be x to the n plus 2, and then we'll have a 4n plus 1, and the same radius of convergence. All right, so I don't know about you, but I think this is kind of fun, right? You manipulate, you start off, and really all we have is geometric series. But from that geometric series, we can find power series representations for all kinds of functions. Now, I'll give you one reason why you might want to represent functions as power series. And we'll talk about this a lot more as time goes on. But I just want to do one last example here. So what I like to do is approximate the integral from 0 to 0.3 of x squared over 1 plus x to the 4th. And I want this to be accurate to 6 decimal places. So let's go correct to 6 decimal places. Here's what we're going to do. We're going to find a power series representation for our integrand, and we're going to integrate that power series. And we'll see what happens. So just off to the side, let's see 1 over 1 plus x to the 4th is going to be 1 over 1 minus the negative x to the 4th, which is going to be sum n equals 0 to infinity, minus 1 to the n x to the 4n. So if I multiply through by x squared over 1 plus x to the 4th is going to be sum n equals 0 to infinity, minus 1 to the n x to the 4n plus 2. So we're going to compute the integral from 0 to 0.3 of the power series, sum n equals 0 to infinity, minus 1 to the n x to the 4n plus 2. Let's see what happens here. So we take the antiderivative. We get sum n equals 0 to infinity, minus 1 to the n, x to the 4n plus 3, divided by 4n plus 3. We're doing a definite integral, so I need to evaluate from 0 to 0.3. All right, so let's plug in our limits of integration, and what we get, this will be sum n equals 0 to infinity, minus 1 to the n. 0.3 is the same as 3/10, so I want to use 3/10 when I do this. So this is going to be a 3 to the 4n plus 3 divided by 10 to the 4n plus 3 times 4n plus 3. So that's what happens when you plug in the upper limit. When you plug in the lower limit, you just get 0. So this definite integral is equal to this. In other words, this infinite series converges to the area under this curve right here. Right? And, okay, so I don't know what this converges to. All I know is that it does converge. And now it says approximate this correct to 6 decimal places. Well, we have two situations where we know how to approximate infinite series, right? If we did with the integral test or the alternating series test. This series converges by the alternating series test. And so I can use that estimation process to approximate this integral, or approximate that integral. So now what do I do? Well, I need to find n, so that 3, so I'm going to substitute an n plus 1, so that'll be a 4n plus 7 divided by 10 to the 4n plus 7 times 4n plus 7. I want to correct to 6 decimal places, so I want 1, 2, 3, 4, 5 zeros. So if it's strictly less than this, then it'll be correct to 6 decimal places. And now I just need to figure out which n does this. And it turns out, you can check, that n equals 1 works. And so, what does that tell us? It tells us that the integral from 0 to 0.3, x squared over 1 plus x to the 4th dx, is not one that I really want to integrate on its own, finding the antiderivative and so on. So by approximating it, what's it equal to? It's equal to the sum n equals 0 to 1. I think I said equals, I meant approximately equals. 3 to the 4n plus 3 over 10 to the 4n plus 3 times 4n plus 3. And what would this give us? Let's see, when n equals 0, I would have 3 cubed over 10 cubed times 3 minus 3 to the 7th over 10 to the 7th times 7. And I don't, it looks like I didn't actually work this out, but by just subtracting these fractions, you'll get an extremely good approximation to this definite integral. And that's it, that's all it takes, is the 0th term and the 1st term. So I find this amazing. Hopefully you do also. And we will definitely see more of this as we go on in the study of power series. So we'll see you next time.